We have prepared tutorial using a Jupyter notebook covering the topics on data cleaning that we explained today. We're not going to execute this now for all of you, because otherwise we are going to basically have n library problems for all the people attending the school. So we have pre-run this notebook. We are going through all the cells of the notebook, but you can try using your laptop to run it. And maybe if you have time, we are going to stay all the week here, so we may discuss this. So, okay, so for this tutorial is basically considering an astronomical dataset, that is a stellar classification dataset taken from SDSS, and so a tabular dataset. I produced from this a dirty version of the dataset in which I artificially added corrupted or missing data, anomalies, outliers. And then we are going to programmatically see some of the topics we covered. So for this, we are going to use a few libraries. Some of them, like Matplotlib, Seaborn, are visualization libraries. Others, like Pandas, scikit-learn, UMAP, are the libraries that allow to load the data set, run some operations with rows and columns, and apply some of the methods, imputation and dimensionality reduction methods. And so you basically install these, and you can try to run it in Colab, or and then we import all of these libraries at the beginning. Okay, I skip this because we are going not to use. I think this is just creating our directory where to run the tutorial and where to download, I think, the dataset. The dataset is available at this link. It contains 100,000 observations of sources from SDSS, taken and measured in various optical bands. And these are the columns that you find in the dataset. We are not going to use all of them. We are just going to use flux variables, so U, G, R, and so forth, and redshift, and the class. So there is a variable called the class, which indicates whether the object is a galaxy, a star, or a quasar. The focus here is not on the dataset or in the astronomical problem, but on just seeing the techniques in action. So okay, the dataset is available in Google Drive. So we have from the link that is commented here, I don't know if you have the original dataset. In this case, we downloaded the dataset, the dirty version of the dataset that I altered, as I said. Okay, we're going to use pandas to load the CSV file. Here, the method is just pd read CSV. And so once you print the loaded dataset, which is a data frame object, you see all the columns that we were mentioning before, the first rows and last rows. And you can see the number of data contains actually 2,000 rows more, because these are the corrupted variables that I added. If you use the data frame info method, you see a summary of your data set, all the columns with the data type. And here we are just going to remove completely from the data set some of the variables, because we are not interested in them. And so here with this method drop, data frame drop, we remove from the data set all these columns, alpha and delta, the celestial coordinates, and some other flag variables, and so forth. And so we print again a summary of the dataset, and we end up with this, basically the object identifier, then flux variables, class, and redshift. We can use the describe method that is basically returning summary of all the variables with the mean, standard deviation, all statistical index. As you can see, Many of these values are not correctly computed because there are missing values that we have added artificially in our table. I think you can, we are going to see them when printing the rows, for sure. So here what we're going to do is producing a complete version of the data set by first replacing, there are also infinite values that we placed randomly. So not a number, also infinite values. And we, in this case, we're encoding all of them with not a number. Here we basically select a subset of this data set that is just containing the complete data. And for this, we recompute again the statistical index. And so here you find the mean, standard deviation, a median, kurtosis, and skewness. And so here, by looking at this data, we just look something. So flux and redshift variables, if you look at the skewness, they are moderately negatively skewed. On the other end, the kurtosis is larger than 0, so it is somehow saying that these variables are peaked and have heavy tails. And these are the data that we are going to use for the tutorial. So first, we're going to perform some of the data integrity check I was mentioning at the beginning of my presentation. They are sort of to-do list of steps to check. One is looking at for missing values and not numbers and infinite values, so corrupted values that may be present in your dataset. And so with this helper method, dump none counts, we see a fraction, how many missing data, none values we have for all the columns. So as you can see, there is a very low fraction of less than 2% of the data are missing data, and these are just limited and restricted to the flux variables, U, G, R, and so forth, Z. Below, we do the same for infinite values, so there are also some corrupted numerical values in the same flux band variables, less than 1%. So we have not corrupted so much the data set. And here we encode again the non-infinite and not a number values as a not a number, so we will effectively treat the infinite as missing data. And a nice way to look visually at these patterns of missing data can be done using Seaborn library or missing no libraries. This library with this method produces a heat map of all your data observations for all the columns. And in this case, the yellow line is indicating the presence of missing values. So here, of course, you have lots of data, like 100,000. So it's somehow some of these lines are compressed. So you may eventually produce a similar plot with a subset of your data set. You can do the same with these missing no packages, which produces a matrix similar to the previous one, in this case of a subset of 1,000 observations. And again, you can see the black lines are indicating a presence of missing data. So from this, you may want to look at possible correlations between of missing data across the columns. And but this can be done probably better using this method of missing no packages that produces a heat map, a correlation map of missing data across the variables. So in this case, we just generated the missing data artificially, randomly, so without any correlation applied. So if there is a missing data in one column, it is not probably happening significantly in the other columns. And so this is why the correlation coefficient here is 0. So we don't have a correlation, which is likely an indication of the data missing at random somehow. Here we look programmatically at duplicated rows. So we know I have added duplicated data. The method is discovering that there are 2,000 duplicated rows. And you can use this method that pandas provide, data frame duplicated, and we can remove them, basically keeping the first, the duplicate set. And so here we end up with a data set that has no duplicated rows. Okay, so we have removed possible corrupted data in this data set. Then we look at unique values. If you remember, this can be a sort of, they can maybe indications or issues with some columns. For example, the object identifier is expected to be a sort of primary key, so you should not have duplicated or non-unique values. So this would be suspicious. And similarly, a high number of duplicated values in flux band columns would be suspicious as well. And so with this helper method that I'm not covering in detail, it's just a matter of, it uses the value counts method of pandas frames. You can plot how many distinct values you have per column. So it's a sort of stats of, so for example, if you look at the first column, we see that we don't have duplicated rows, so we have all singleton rows. That's okay. And for the other, we have, of course, some duplicates that are basically none because we have not removed them or handled them at the moment. And then there are, of course, some moderate duplication for the other columns. Okay. Here we detect misannotations. So we have a categorical class variable that is indicating if an object is a star class or a star, quasar, or galaxy. We see here we have added. We see that with this method value counts that we used before, we see that there are values that are there is a mismatch of the notation used for labeling the data. Like some notation uses upper class, some lower case, some add forgot or add a trailing space in this case. So we have, if we understand that these are all labels that should represent the same category object, we can maybe fix this just with this string based method. So we strip training spaces and we convert all in uppercase, and we have 3 categories for all the data, for all the unique data set. This may sound trivial, but assume, for example, that this data set was produced from different releases or by different person, one colleague, for example, they uses annotation, then you start to use because you take this data set from a new epoch of data, and then you start to use a different notation, then you merge the 2 data sets. This is something it might happen actually. Yes. Do we have questions on this?
Till here, so it's just nothing. We just look at the data, let's say how they are. We put the notebook, you can see it on the Indico page as well, but the fact is that for the data loading, it takes a bit time, so maybe you cannot live run the cells and follow here. But if you have also a question, I can also go through the whole as you wish. So till here, everything was clear? I think they are all sleeping.
Okay, let's now run a visual analysis. So we're going to look at the distribution of the variables and plot and compute some correlation between them. Here we first apply a log transform to our data, our numerical data. We are excluding the classes from these transforms. We log transform them and basically transforming them in range 0, 1 in a logarithmic transform, but we are encoding also in some part of the notebook missing data with negative values. So in this case, we know that all the data have a range 0, 1, and in some case we put missing data in -1. Okay, first the class distribution is the easiest one to be plotted. And this is telling us, these are just sort of matplotlib stuff, so I think it's not worth to spend time on this. We just visualize one column of the data, the class column, and we already see that the data are unbalanced because we have a large proportion of galaxies and a smaller proportion of stars. So this is something you should look at the beginning and before maybe thinking about training the model, or maybe thinking to rebalance the data set afterwards if your model is not able to predicting well the star category and so forth. So these are sort of diagnostic plots that you should make at the beginning. Then we look at redshift and band flux distribution. We can see, okay, quasars have a higher redshift in this case and higher flux in the other cases. This is the negative skew that we will see before. In these plots, I basically put all the missing data into -1 just for the sake of plotting. So not because I'm inputting them with -1. Okay, then we look at two-dimensional variables with scatter plots. I've added in the notebook two possible methods to compute correlation coefficient. So Pandas is giving you for free a method that is correlation. So you apply the method to your data frame and you select which correlation coefficient you want to compute, Person, Spearman, Kendall, and so forth. SciPy does the same, and it gives you also, I think, the p-value of the test. So I've added all the both methods in the notebook, but they are doing the same. So if you print here, you can get a correlation matrix, basically, with Pandas and SciPy. And we are going to plot them. This is a very long draw methods to produce this plot. So don't spend time on this. So these are the plots we were seeing in the presentation, so correlation plots, and I have added in the upper triangular part the values of the correlation coefficients. So this is what we obtain for a subset of the data set, but we can do the same also for plotting all the data sets, so 100,000 rows. In this case, I changed the scatter plot to two-dimensional histograms, colored histograms. So we just look from this that there is high correlation. So some of the variables after log transforming the data are quite linearly correlated. And this is what the correlation coefficients are also telling us. I mean, the band flux variables. We can do the same and look at the correlations overall and also for data divided into different classes. So this is a correlation map for all the data, regardless of the class that you have. And you can see the high values of correlation for flux band variables, and not less smaller correlation for the redshift versus the fluxes. But we can also plot, understand, and analyze the correlation as a function of the class. So this is the same plot, but for a subset of the data that are labeled as galaxies. Galaxies, quasars, and star. Here you can see and have an indication of how the correlation is changing eventually between across your class. And this is just done using, I think, a method of Pandas. Let me check. Yes, or Seaborn in this case. Heat map, and then you pass the correlation matrix that is computed using the core method of Pandas. Okay. So, any question on this? Most visualization diagnostics. So here we are going to look at the dimensionality reduction. So if we are okay, we continue. Ok? Vuoi andare tu? Faccio io? Ok. Okay, now we want to see our dimensionality reduction methods in action, in this case PCA, UMAP, and TISNE. And we are going to project this data, so the band, flux, and the redshift, into a two-dimensional space embedding. For this, we first set some additional data frames that we use for the projection, because I want to actually show the projection for different input data. So we produce three kinds of input data. So one is the original data that we have. Another one is the original data after transforming them with a logarithmic transform. And then the similar data set, so log transformed data, in which the not number values are encoded with the -1. So in the first case, we basically removed them from the data set with the listwise deletion. In the last one, we just set them to -1. And we will see the resulting embeddings. So these are helper methods, plot embeddings to just plot with matplotlib the two-dimensional scatter plot. We are going to use the same method for all the dimensionality reduction methods, PCA, UMAP, and TISNE. This is something where Farida was mentioning before. So scikit-learn has this similar API for different models, and it is basically applied to different objects, in this case a PCA object, and it has the fit and the transform and fit transform method. So in this case, you define a PCA object, you select how many components, principal component you want to retain at the end. In this case, 2. We are just looking at the 2 major components. But you can also do in the commented code here another criteria. So for example, retain as many components until reaching more than 90% of the variance. In this case, if you pass a floating point value, this is interpreted like this. And then we run this method, fit transform. So the method is basically computing the PCA and transforming the original data in the embedding space, this X embed. And then there are methods to retrieve how many components, what is the explained variance ratio, and that's it. Once we have the embedding, we can plot the embeddings for the 3 subset of data set we have produced, and this is the results. So these are the original data, so not nonce values were excluded. As you can see, there is a sort of clustering of the data, but the clustering are somehow merged or overlapping. In this case, we have log transformed the data. And so you can see that probably we can maybe even select one variable as a remaining data set because there is very strong linear correlation here for stars. If we leave, of course, not number values encoded to -1, you can have all these sort of spurious clusters that are due to the fact that most of the data are between 0 and 1, and then there are some artificial not number values set to -1. This corrupting. So this is just for looking at the data, but don't do that, of course. We are going to see this on with the other dimensionality reduction after we input the missing data. Let's see what UMAP is doing. So UMAP library follow a similar API than scikit-learn. So you define an object, UMAP, you pass a series of hyperparameters like number of components of the embedding, number of neighbors, and the minimum distance. If you recall, if you remember, are the parameters that the method is requiring, and it is sensitive to, and the random state, which is a seed that you can use for reproducibility. And again, we do the same on of the PCA. We use the fit transform on the 3 dataset, and this is the UMAP projection. So these are the original data. You can see actually how it separated particularly well the quasars. This is what happens with the log transformed data, and it seems that log transformation helped somehow separation between the classes, particularly for stars. Here, okay, we see this sort of spurious plot that are related to the minus, to the nonce encoded as -1. Okay, let's look at Disney. Similar API, Disney object, number of parameter, number of components too, perplexity value. You can play in your notebook with this, changing the values and see the plot. All of these steps are requiring quite some time, so this was one of the reasons why we didn't run the notebook live, because these are, so particularly Disney, which is it's very slow, and we have a large data set of 100,000, so it is taking time to do this for 3 versions of our data set. Here we can see the original data, transformed data. Here you can see how a better embedding was obtained with this method. And again, these sort of spurious clusters having the nonce. Okay, so far, any question?
Just a curiosity, how frustrating? Just a curiosity, how frustrating can be playing with perplexity and all the parameters you want to tune to get a proper separation?
Sorry, how?
How frustrating? I mean,
I think it's very frustrating. So I mean, I mostly use the UMAP, and you need to have labeled data, as I was saying before, because consider, for example, this same plot in which you have any indications about the class. So for me, it's like most useful for visualization scopes. Even if I'm aware, for example, some colleagues in Catania, they use this as a sort of pre-processing step before applying clustering algorithm. This is kind of debated, and so in their analysis, they didn't have any labels. So they spend basically a lot of time looking at these embeddings. In this case, they were working not with the tabular data, but with the images. And so they were looking at the images with 3 channels and see if actually the embeddings were somehow clustering in a meaningful way the data. So we have produced in a project a sort of a graphical tool that allows to do that with images. So to produce embeddings and see graphically superimpose the images in the embedding plane and see if actually this is meaningful. But yes, this is tricky. I mean, I typically run the UMAP with different settings and then see if I have to say that most of the data are not clustered. So I mean, in the application that I did are not clustering like this. So it's kind of ideal. I typically just obtain blocks or very small clusters that are difficult to interpret.
And if I can add, maybe it's a good practice for data that they are a lot, like you sample randomly, like and take a subset of your data and you try many times, like do a kind of grid search for the parameter of your model on a subset of the data. Because, for example, for this, if you need to run the 100,000, it takes a lot. But you can do a subset and do a kind of grid search to, like, you run a job, you go home, the day after you come and check.
I have a very naive question. My question is about the normalization. For example, if I have just one source,
Spento forse.
Sì, spento.
works? Okay. And if I have just one source for my table, my data, by definition, these data are already normalized by themselves, modulo a scale factor. So I don't know in this case if it's really needed to normalize them.
Okay. What do you mean by one source?
For example, I have a very homogeneous data set coming from a single analysis or a single source, and all the data are computed in a way that are the relative, ratios between the data, or the interaction between data are the same, are self-consistent inside this table.
I think it's exactly the steps are you visualize. So you plot the distribution of your data. If it's normalized, of course, you don't need to normalize them once again. So first you do the visualization, plotting them properly, like with whatever type of the data it needs that kind of plotting. And then you do the data cleaning and the transformation. Like transformation, it comes after. Like it's one step before training your machine learning method.
All right. And also I have a comment. I'm working on variable stars and trying to find automatically variable stars after a Fourier analysis. So I have a kind of a plane where the variable stars more or less are located in a specific area. I think that probably a PCA analysis could help a lot in this case. So I
don't know exactly the field, but you can try. Yes, of course.
Okay, maybe I can use exactly this notebook and try to adapt.
Yeah. Once you have a tabular data set, CSV or ASCII or whatever, you can import this with pandas, and the rest of the steps are similar.
All right.
So.
Okay.
Yeah, let us know.
Yeah,
Very cool.
If you want, we can also discuss like these days as well.
All right.
Yeah,
Thanks a lot.
Sure.
Just something about the normalization. Even if your data are really compact and you think that they share the same kind of structure, the same relationship, one problem is if you are using more than one feature, if they do not share the same dynamical range. For all the set of features that you are using, if they span more or less in the same dynamical range, for most of the model, it's almost the same. But even if one by one, you think that they are, let's say, normalized, not normalized, the fact that one can span in a different way could affect a lot of models. So, for instance, basically, if you have, for cat and dogs, the length of the tails and the weights, even if one single variable seems reasonable, the fact that weights are in kilos and the length is in millimeters, the dynamical range is about 1 from 100 for the length and 1 from 1 to 7 for the weights. And therefore, it affects a lot of methods that are based on distance or vectorial product and so on and so forth. Yeah.
Yes. Yeah. Good point. Yes. Yes. I did. I have the same for in an application I did 2 years ago. So in this case, I have an image with 3 channels, so radio and infrared at different. So the infrared was very dominant, so I have a larger dynamic range with respect to the radio. And so the model was basically without normalization or rescaling. The model was learning basically only the infrared, not the radio. So this is what Stefano was saying. It's a very, very common case. We are out of time. Okay, try to go quickly on that. Data cleaning, here we will see 2 steps. So the last 2 are left for you once we cover the LOF and isolation forest. So first, extreme outlier identification, so very statistical based. There is a method, box plot, that is able to produce the plot I was mentioning in the slides. And here you can easily see that there are lots of outliers that I artificially added to the data, the data that are outside the whiskers. What we do, we apply the interquartile range method. That is simpler. We compute basically the interquartile range, the first and third quartile, lower upper bound. We plot them. And we basically select here the data that have data within the bounds. In this case, we increased the bound to 3, so we are detecting the very extreme outliers. And after we remove them from the data, we are left with this. So we have removed all of this method. We can remove them, or in alternative, the notebook does an alternative processing. So it basically converts them to missing values, so to not a number. So we still keep them, but if we know that they are like corrupted measurement, or we can maybe decide to set to none values and input them in a second step. And this is what we are doing here. Okay, so here we replace some of these values with not numbers. Okay, and so we have left all of this data with some of the outliers encoded as none. So we have now a large collection of missing data to be inputted. For this, we use this scikit-learn iterative inputter, which does this. So there is an helper method that calls this iterative inputter class of scikit-learn. You can use different estimators. So the standard one is a regression method, but you can change it. And you can start from a median imputation and then iteratively do regression imputation. You can do single imputation, as in this case by default, by setting stochastic to false. If you set it to true, you do a stochastic regression, what we have seen in the slides. And if you run these multiple times and produce multiple completed data set, you can do multiple imputation. And also in this case, you have this classical fit transform method. So it's very recurrent API. Here we took the data set from the previous stage and we input the data. So we produced a new matrix or a new data frame in which we have inputted the data with the. So this is the original data set in which you still see the nonce, and here we print the complete data set in which the nonce were replaced with the regression imputation. So we look again at the scatter plots of all the data. This is the complete set having all the variables inputted. And we finally perform a complete UMAP embeddings of the finally cleaned data. So this is the result. So you have these 3 larger blobs of having all the data. Before we were just plotting the data without the nulls, so using list-wise selection. Now we have kept all the dimensionality of the data set with imputation.